Welcome to a journey into quantum mechanics, focusing on the double slit experiment, a pivotal concept in quantum physics. The double slit experiment has a rich history. In 1801, Thomas Young used light to demonstrate wave interference. Later, in 1909, G.I. Taylor showed that individual photons interfere with themselves, even with faint light. In 1961, Claus Johnson used electrons to confirm the wave-particle duality of matter. Finally, Murley et al.'s 1974 experiment showed that an interference pattern emerges even when single electrons are sent one at a time, proving quantum superposition. The experimental setup consists of a coherent source, an opaque barrier with two narrow slits, and a detection screen. The coherent source releases particles toward the barrier. The particles pass through the slits and then strike the screen, where their final positions are recorded. Wave interference comes in two forms: constructive and destructive. Constructive interference occurs when waves arrive in phase, crest meeting crest, adding amplitudes to produce a bright fringe. Destructive interference happens when waves arrive out of phase, crest meeting trough, canceling amplitudes to produce a dark fringe. The mathematical description for constructive and destructive interference are provided below. The experiment reveals a quantum paradox. When both slits are open and no detector is present, particles behave like waves, creating an interference pattern. When a detector is turned on to observe which slit the particle passes through, the interference pattern vanishes, and particles act like classical objects. Removing the detector brings back the wave behavior and the interference pattern, suggesting observation itself alters quantum reality. This paradox is rooted in wave-particle duality. Superposition states a particle exists in all states simultaneously until observed. The wave function describes the probability of finding the particle at any location. Measurement causes the wave function to collapse into a definite state, changing reality. The principle of complementarity states that wave and particle aspects are mutually exclusive. Observing one destroys the other. Here is the mathematical description for the double slit experiment. The path difference determines the fringe type. Bright fringes occur when the path difference equals $m Dark fringes occur when the path difference equals $m plus frac 1 lambda. Fringe spacing is calculated using $text y equals text m lambda text l slash text d $. The de Broglie wavelength relates wavelength to momentum, while the uncertainty principle limits the precision of simultaneously knowing position and momentum. The double slit experiment has profound modern implications. In quantum computing, superposition and entanglement are exploited for faster computation. Electron microscopy uses the wave nature of electrons for sub-nanometer imaging. Quantum cryptography utilizes the measurement collapse effect to detect eavesdropping. Finally, the many worlds interpretation suggests that every quantum event branches the universe into parallel realities. Let's summarize the key takeaways. First, light and matter exhibit both wave and particle properties, depending on how they are observed. Second, single particles show quantum superposition by building up an interference pattern. Third, the act of measurement alters the system. Fourth, this experiment is the conceptual foundation of modern quantum mechanics. Finally, classical intuitions break down at the quantum scale, where probability governs nature. As Richard Feynman famously said, if you think you understand quantum mechanics, you don't understand quantum mechanics. The double slit experiment is truly the foundation of modern science. Thank you for watching this video. If you found it helpful, please subscribe, like, and share it with your friends. You can also join our community and follow us for updates on new videos and topics.